Hi, my name is Tom Sandry. I'm the Director of Technical Support here at Protec Equipment Resources, and I'd like to welcome everyone to the Battery Testing and Maintenance webinar. This webinar recorded version is going to be broken into a couple different parts just to break it down into a more playable format. But in this training course, we will see that a battery plays a very critical role and is a complex electrochemical device. Terms and definitions associated with batteries and battery components will be reviewed and discussed, along with a review of various failure modes. Batteries require maintenance and care to ensure their state of health. Different levels of maintenance, various testing methods, along with data analysis will be discussed. We will also review the NERC PRC 005-1 and the NERC PRC 005-2 draft. Now, our objectives of this course will be for students will learn to identify various types of stationary batteries, the construction and the application of batteries. We'll be able to define safety related to the batteries and testing, be able to define failure modes, define and explain the value of testing and inspection procedures, and students will learn how to interpret data and analysis of test results. Our program outline will first start with learning basic terms and definitions, types of batteries, the battery construction, safety as related to batteries, storage, shelf life, inspection, installation, failure modes, test and inspection, data analysis, a review of the NERC reliability standard, protection and control PRC 005, and we will also provide a link to a download knowledge test. We're going to start with the terms and definitions. A battery is a device that converts the chemical energy contained in its active material into electrical energy by means of an electrochemical reaction. While the term battery is often used, the basic electrochemical element being referred to is the cell. A battery consists of two or more cells electrically connected in series to form a unit. In common usage, the term battery and cell are used interchangeably. A single lead-acid cell can deliver a maximum potential difference of about 2 volts under load. Therefore, a 6-volt jar is made up of 3 cells connected in series. A 12-volt jar is made up of 6 cells connected in series, and a 120-volt battery combines 60 cells all connected in series. Now, a jar is a term that refers to the container in which the cells are housed. The earliest cells were contained in glass jars. Capacity. The most common term used to describe a battery's ability to deliver current is its rated capacity. Manufacturers frequently specify the rated capacity of their batteries in ampere hours at a specific discharge rate. Example: 25 amps for 8 hours would equal 200 ampere hours of capacity. Battery capacity varies with the discharge rate. The higher the discharge rate, the lower the cell's capacity. Lower discharge rates result in higher capacity. The rated capacity for lead-acid batteries is usually specified at either 8, 10, or 20 hours. UPS batteries are typically rated at 8-hour capacities. Telecommunication batteries are typically rated at 10-hour capacities. Electrolyte. An electrolyte is any substance containing free ions that behave as an electrically conductive medium. With flooded lead-acid batteries, electrolyte consists of the water and the sulfuric acid. In gel cells, gelified electrolyte, the sulfuric acid is mixed with a silica fume, which makes the resulting mass gel-like and immobile. On AGM sealed cells, the electrolyte is absorbed into a mass of fine glass fibers. the term end voltage. In batteries, the end voltage is the prescribed lower limit voltage at which battery discharge is considered complete. The end voltage is usually chosen so that the maximum useful capacity of the battery is achieved. The end voltage is different from one battery to the other and is highly dependent upon the type of battery and the kind of service in which the battery is used. A completely discharged lead-acid cell has a potential difference of about 1.75 volts, depending on the rate of discharge. Other terms commonly used for end voltage is final voltage and/or cutoff voltage. Float voltage refers to the voltage that is applied continuously to a cell to maintain the cell in a fully charged condition. The proper float voltage depends on battery chemistry, construction, and ambient temperature. Low float voltage equals a not fully charged cell. And a cell that is not fully charged cannot supply full capacity and can lead to plate sulfation, which can become a failure mode. A high float voltage equals overcharging of a cell. Overcharging of a cell results in cooking the battery or cell, elevated or higher internal temperatures. This can lead to grid corrosion, thermal runaway, and dryout, which are all failure mechanisms. Float current. Float current is a DC current that flows through each cell. It is the interaction between the float voltage and the cell's internal resistance. It is supplied by the charger. Electrochemical process reversed, and lead sulfate on plates converted to sulfuric acid and active material. A high float current can be a precursor to thermal runaway, and a high float current can be a resultant of shorted cells, could be a resultant of ground faults, or a high float voltage. OCV is the acronym for open circuit voltage. Open circuit voltage is measured during storage, installation, and commissioning of cells. After cells are installed into a battery string, the sum of all cell voltages must equal the total string voltage. For example, if we string 3 cells together, we should have a resultant of 6 volts at the open circuit voltage on the terminals. SOC is the acronym for state of charge. Keep in mind that a battery that is charged means nothing about supplying load as designed. An example, a car battery can be fully charged, but can still not deliver the rated current to start the engine. Fully charged is important, but means nothing about the cell's capacity. Specific gravity is an indicator of state of charge. Also, open circuit voltage can be used to determine state of charge in a sealed cell. SOH is the acronym for state of health of a battery or a cell. The state of health reflects the general condition of a battery and its ability to deliver the specified performance compared with a fresh battery. It takes into account such factors as charge acceptance, internal impedance, voltage, and self-discharge. During the lifetime of a battery, its performance or health tends to deteriorate gradually due to irreversible physical and chemical changes, which take place with usage and with age until eventually the battery is no longer usable or dead. The state of health is an indicator of the point which has been reached in the life cycle of the battery or cell, and a measure of its condition relative to a fresh battery or cell. State of health is also an indicator of capacity. As the internal impedance of a cell increases, capacity decreases. Specific gravity is the ratio of the weight of a solution to the weight of an equal volume of water at a specified temperature. Specific gravity is used as an indicator of the state of charge of a cell or a battery. Specific gravity measurements cannot determine a battery's capacity. The specific gravity decreases during the discharge of a battery to a value near that of pure water, and specific gravity increases during the recharging of the battery or cell. The battery is considered fully charged when the specific gravity reaches its highest possible value. Specific gravity does vary with temperature and the quantity of electrolyte in a cell. When the electrolyte is near the low level mark, the specific gravity is higher than normal and drops as water is added to the cell to bring the electrolyte to the full level. The volume of electrolyte expands as temperature rises and contracts as temperature decreases. As the volume of electrolyte expands, specific gravity readings are lowered, and conversely, specific gravity increases with colder temperatures. The specific gravity for a given battery is determined by the application it will be used in, taking into account operating temperature and battery life. Some examples of specific gravity values. Value of 1.3 typically would result in a highly cycled battery such as those for electric vehicles. 1.26 is a value commonly found or associated with automotive batteries. 1.25 typically associated with UPS, standby and high momentary current discharge requirements. 1.215 general applications such as power utilities and telephone applications. In a selection of battery for a given application, some of the effects of high or low specific gravities to be considered are: with high gravity, you tend to get more capacity, but at the result of a shorter life. Less space is required with cells of higher specific gravity. Higher momentary discharge rates. These are also less applicable to float operations and have more standing losses. Cells with lower gravity typically provide less capacity but provide longer life. There's more space required at the lower gravities, lower momentary discharge rates, but these cells are more adaptable to floating operations and have less standing loss. The term pilot cell. One cell in a battery is usually selected as a pilot cell for specific gravity readings. Since all cells of the batteries receive the same amount of charge or discharge current, the specific gravities will fall or rise proportionally to that of the pilot cell. It is advisable to change the pilot cell after about 10 readings, because a slight amount of the electrolyte is lost each time a hydrometer reading is taken. Ripple current. Ripple current is due to a lack of filtering on chargers and rectifiers. It is an artifact of the AC input line voltage. Over time, continuous ripple current may shorten battery life due to battery heating or cycling due to a charge-discharge caused by the AC frequency. The IEEE recommends that ripple current does not exceed 5 amps for every 100 ampere hours of battery capacity. The less the ripple current is, the better the battery life will be due to the ripple current effects. Now, since heating is a cause of thermal runaway in valve-regulated lead-acid or sealed cells, the IEEE 1188 document recommends and calls out the usage of ripple current measurements. Temperature effects. Chemical reactions internal to the battery are driven either by voltage or temperature. The hotter the battery, the faster chemical reactions will occur. High temperatures can thus provide increased performance, but at the same time, the rate of the unwanted chemical reactions will increase, resulting in a corresponding loss of overall battery life. The shelf life and charge retention depend on the shelf discharge rate, and shelf discharge is a result of unwanted chemical reactions in the cell. Temperature therefore affects both shelf life and the cycle life, as well as charge retention, since they are all due to chemical reactions. For every 10 degrees above 77 degrees Fahrenheit, a lead-acid battery's life is cut in half. Series connections. When we connect a positive terminal of one cell or battery to the negative terminal of another cell or battery, we are connecting the batteries or cells in a series string. When connected in a series string, the cell voltages will add, but the ampere hours or capacity will stay the same. For an example, if we were to take 4 12-volt battery jars and connect them in series, the ampere hours of 25 ampere hours would remain the same, but the voltages of the jars would add to a total of 48 volts. If we were to connect the jars or the battery cells in parallel, where we connect from positive terminal on one battery or cell to the positive terminal of another battery or cell, in a parallel configuration, the voltages of each cell or jar will result in the same value in the parallel string, but the ampere hours will add. For an example, if we were to take 4 12-volt jars, connect them in parallel, our terminal voltage would still be 12 volts, but the 25 ampere hour of each jar would add, providing 100 ampere hours of overall capacity. Ampere hours. Ampere hours is the quantity of electricity the battery can deliver. Typically used in telecom and utilities, this is expressed in ampere hours at an 8-hour rate to a cutoff voltage of 1.75 volts at a temperature of 77 degrees Fahrenheit. Now, an example, when we have a battery carrying a model number of MCT2-4000, 4000 is typically designated as the ampere hours at an 8-hour discharge rate. So we would have 500 amps for 8 hours. Now, another example may be a model number of 3DJ-200, where this particular battery will deliver 25 amps for a total of 8 hours, or 25 times 8 equals 200 ampere hours. And again, the term ampere hours, we will find that very common with batteries associated with telecom or utility applications. Watts per cell is a term that we will find more commonly used when referring to UPS batteries. And a classic example of a UPS style battery may be a model UPS 12-700 MRF. The UPS 12 referring to a 12-volt battery, 700 would be the watts per cell. And at 700 watts per cell at a 15-minute rate to a cutoff voltage of 1.67 volts per cell at a temperature of 77 degrees Fahrenheit. Term duty cycle and depth of discharge, or DOD. Duty cycle basically refers to how many times can a battery or cell be charged and discharged. The depth of the discharge is critical to the overall battery life. A battery can generally withstand a much larger proportion of shallow cycles. For an example, 100 cycles at a 5% depth is less harmful than 5 cycles to a 100% depth. Therefore, the depth of discharge is the amount of energy that is removed from a battery, and it is expressed as a percentage of the total capacity of the battery. And that concludes the terms and definitions portion of the presentation. Okay, next we're going to go into and discuss types of batteries. Now, in discussing types of batteries, we're going to keep it relatively simple to the primary batteries, Primary batteries, these are typically your non-rechargeable, throwaway type of batteries, generally seen in watches, cameras, transistor radios, etc. The ones that we're going to be focusing on more in this webinar is the secondary batteries. Secondary batteries are the rechargeable style batteries. They can either be portable or they can be stationary. Now, in secondary batteries, we can have small UPS devices, typically used for home and office equipment. We can have large uninterruptible power supply or UPS systems, typically used at data centers, supporting critical process equipment, healthcare systems. And these batteries can be backup power for controls in the utility system. UPS systems are typically power quality driven systems. Now, types of batteries and battery requirements. Depending upon the construction of the battery, we can have batteries that are designed for short duration requirements. And in short duration requirements, this is where the battery discharges in seconds or a few minutes. For instance, this may be used for computer system shutdown. It could be where the battery merely has to deliver current just for a short period of time as a ride through until a generator comes online. Again, a lot of your UPS systems are based on short duration, high discharge rate battery systems. Long duration requirements is where the battery system needs to be able to discharge or deliver its rated current over a long duration of time or a long period of time, typically defined in hours. And we will normally find long duration requirements when dealing with like substations or utility or telecommunication style batteries. Both the short and the long-term requirements are going to be dependent upon the way the cell is constructed. Now, different types of secondary batteries. We have the lead-acid style batteries, and lead-acid style batteries can be either of a flooded or of a sealed type of construction. You have nickel-cadmium, which again, the NiCads or nickel-cadmiums can also be either of a flooded or of a sealed construction. And you have other chemistries, for instance, lithium ions or nickel metal hydride. Flooded cells are those where the electrode plates are immersed in an electrolyte. Since gases created during charging are vented to the atmosphere, distilled water must be added occasionally to bring the electrolyte back to its required level. Here we see an example of a lead-acid jar, and we notice that typically in a flooded, we are using a clear style jar where we can actually visibly see into the electrolyte and into the plates. On sealed lead-acid batteries, these types of batteries confine the electrolyte but have a vent or valve to allow gases to escape if internal pressures exceed a certain threshold. During charging, a lead-acid battery generates oxygen gas at the positive electrode. Sealed lead-acid batteries are designed so that the oxygen generated during charging is captured and recombined in the battery. This is called an oxygen recombination cycle and works well as long as the charge rate is not too high. A too high of a charge rate may result in a case rupture, thermal runaway, or internal mechanical damage. And here in our sample of a sealed cell, we see that the jar in a sealed cell is typically a solid or opaque jar where we cannot view into the internal electrolyte material or to the plate construction. Now, flooded cells are very widely used, particularly in utility applications and in many telecommunication applications. They tend to be very, very reliable and very, very long-lasting batteries or cells. The sealed cells, these are the valve-regulated style batteries, and they come as either gel cells or AGMs. Sealed cells typically require less physical space than the flooded style cells, and will typically be used in areas where space requirements may be an issue. For instance, in many UPS systems, sealed cells are the preferred. Sealed batteries are physically smaller and they have less volume of electrolyte. A gel cell is a valve-regulated lead-acid or VRLA battery with a gelified electrolyte. The sulfuric acid is mixed with a silica fume, which makes the resulting mass gel-like and immobile. Unlike a traditional wet cell lead-acid battery, these batteries do not need to be kept upright. In addition, gel batteries virtually eliminate the electrolyte evaporation, spillage, which is associated a lot of times with the flooded cells. They also boast a much greater resistance to extreme temperatures and also to shock and vibration. Chemically, they are the same as wet batteries, except that the autonomy in the lead plates is replaced by calcium. This preserves the mechanical characteristics but renders the construction far less prone to gassing. The battery type is often referred to as a lead-calcium battery. The absorbent glass mat, or AGM, is a class of valve-regulated lead-acid battery in which the electrolyte is absorbed into a mat of fine glass fibers. The AGM's unique construction allows for the lead in their plates to be much purer, as they no longer need to support their own weight as in a traditional cell. Their internal resistance is lower than traditional cells due to plate proximity, and the purer lead plates have a lower resistivity. They handle higher temperatures better and self-discharge more slowly. And that's just a quick overview of some various battery types. Now we'll move straight into the battery construction. Basic lead-acid cell construction would consist of a positive plate, a negative plate, and an acid in order to form the electrolyte. A very, very simple example of this would be the lemon battery, where we use a copper penny to create the positive plate, a zinc nail to create the negative plate, and we use the lemon juice as our electrolyte or our acid. Negative and positive plate construction. The simplest method for the construction of lead-acid battery electrodes is the Protec plate, named after the inventor of the lead-acid battery. A Protec plate is merely a flat plate composed of pure lead. Capacity of a lead-acid battery is proportional to the surface area of the electrodes that is exposed to the electrolyte. Therefore, various schemes are employed to increase the surface area of the electrode per unit volume or weight. A commonly used method to increase the surface area is to make the active material into a paste that acts like a sponge where the electrolyte fills all the pores. A paste or active material is mounted into a frame or grid structure that mechanically supports it and serves as the electrical conductor carrying the current during both the charge and discharge cycle. The most commonly used plates is the pasted plate, and also referred to as the flat plate. The plate construction is used as the negative electrode plate in almost all cases and serves as the positive plate in most standby applications. Positive electrodes are usually of pasted plate or tubular construction. Tubular electrodes are popular positive plates for heavy cycling applications. Tubular constructions uses a frame structure consisting of a series of vertical spines connected to a common bus. The grid structure in both pasted and tubular plate batteries is made from a lead alloy. A pure lead grid structure is not strong enough by itself to handle to stand vertically while supporting the active material. Other metals in small quantities are alloyed with lead for added strength and improved electrical properties. Common alloy metals are antimony, calcium, tin, and selenium. The most common alloys used today are antimony and calcium. Batteries with these type of grids are sometimes called a lead antimony or a lead calcium style battery. Lead calciums. Lead calcium batteries have lower self-discharge rates and therefore will draw less current while on float charge than lead antimony batteries. Lead calcium positive plates may grow in length and width because of grid oxidation at the grain boundaries. The oxidation is usually caused by long-term overcharging, which is common for UPS or other batteries on a constant float charging. Lead antimony batteries can be deep cycled more times than lead calcium batteries. Flooded lead antimony batteries require more frequent maintenance as they near their end of life, since they use an increasing amount of water and require periodic equalization charges. A little more discussion on plates. Regardless of the plate type used, the capacity of any battery is increased by adding multiple plates in parallel. Thickness and number of plates determine the characteristics. If we have many thin plates, the resultant construction will typically provide a high cycle, short duration discharge, typically found in 15-minute UPS batteries. Fewer but thicker plates will typically result in a construction that delivers lower cycle, longer duration or longer discharge rates, and these are typically common in utility or substation style batteries. If we look at the battery discharge cycle, we see that at fully charged, specific gravity will be at its highest possible point, and our electrolyte will be mostly acid. When the sulfates leave the electrolyte and combine onto the plates, the oxygen leaves positive plates with electrolyte. And as the battery begins to discharge, the sulfation develops, or sulfates develop on the plates, removing from the electrolyte, and the specific gravity begins to drop or becomes to the state of water. So again, in the discharging cycle, basically what we're having here is the chemical process of the sulfates leaving the lead acid, forming onto the plate structure, and specific gravity dropping from its highest potential to its lowest potential point. In a battery charging, the reverse is taking place. In a battery charging situation, the sulfates are leaving the plates, recombining with the electrolyte, and specific gravity is going from its lowest possible point back to a point of its highest potential value, indicating that we have mostly acid in the electrolyte. Next, we're going to go in and discuss a little bit of safety. Now, when dealing with safety, safety must be the first thing thought about and discussed before working on battery systems. Safety is never minimized due to time or cost. Battery rooms must always be kept clean, free of obstacles which may impede ingress. Safety problems associated with lead-acid batteries include spills of sulfuric acid, potential explosions from the generation of hydrogen and oxygen, generation of toxic gases such as arson and stibine. Maintenance on batteries should always be carried out by qualified personnel. Now, the NEC definition of a qualified personnel is one who has the skills and knowledge related to the construction and operation of the electrical requirement and installations and has received safety training to recognize and to avoid hazards involved. Proper protective equipment, or PPE, as defined by OSHA, must always be worn. Wearing a face shield or and plastic or rubber aprons and gloves when handling acid is recommended to avoid chemical burns of the sulfuric acid. There should always be a fire extinguisher within the vicinity of the battery room or inside the battery room. An eye wash station where we can flush immediately and thoroughly with clean water if acid gets into the eye, skin, or on the clothing, and obtain medical attention when eyes are affected. An acid neutralizer, typically a bicarbonate of soda solution, can act as a neutralizer for acids in the event of accidental spills. We should be using insulated tools, and we should never lay tools on other metallic objects or near the battery terminals. We should avoid wearing metallic objects such as wristwatches, bracelets, rings, anything that can be conductive. Gelled or liquid coming from a valve-regulated lead-acid battery is electrolyte, which contains diluted sulfuric acid. This can be harmful to the skin and eyes. It is electrically conductive and it is corrosive. Here we basically see a picture of a well-executed, safe environment. We see protective face shield being worn, protective apron for any type of acid spills, rubber gloves being utilized. We see that the battery rack is in a nice, clean manner, good, secure struts, support mechanisms. Okay, the basic safety do-nots. Do not bring heat or flame sources near batteries. Do not remove flame arrestor vents or pressure release valves. Do not lift cells by their posts. Do not remove lead coating or expose copper from posts or connectors. Do not over-torque connections. Do not throw away lead-acid batteries with the common trash. Do not place any battery in airtight area with no ventilation. With good air circulation around a battery, hydrogen accumulation is normally not a problem. If relatively large batteries are confined in small rooms, exhaust fans should be installed to vent the room constantly or to be turned on automatically when hydrogen accumulation exceeds 20% of the lower explosive limit, or the LEL. Battery boxes should also be vented to the atmosphere. Sparks or flame can ignite hydrogen mixtures above the LEL. To prevent ignition, electrical sources of arcs, sparks, or flames should be mounted in explosion-proof metal boxes. A potential for explosion arises when hydrogen gas is created during normal operation inside lead-acid batteries reaches a specific hydrogen-oxygen concentration. Flame arrestors control these flammable situations. The arrestors are designed to control the release rate of the hydrogen gas from the battery and prohibit the passage of an external flame front into the internal chamber of the battery. They also provide a location to add water. They also provide a location in order to conduct tests such as specific gravity and temperature. Here we see a few of the OSHA safety standards related to batteries. The OSHA 126.403, battery rooms and battery charging. 1910.178, charging and changing of batteries. 1910.305, storage of batteries. 151, medical service and first aid. 1910 subpart 1, PPE, and 1910.331 through 335, electrical safety. And here we see again some of the recommended practices and safety governing documents. The NFPA 70, which includes the NEC or National Electrical Code. The NFPA is the National Fire Protection Association. We also have various IEEE recommended practices. The IEEE 450, which is the recommended practice for maintenance testing and replacement of vented lead-acid batteries in stationary applications. 484, the recommended practice for installation, design, and implementation of vented lead-acid batteries for stationary applications. 1187, recommended practice for installation, design, and installation of valve-regulated lead-acid storage batteries for stationary applications. And finally, 1188, the recommended practice for maintenance, testing, and replacement of valve-regulated lead-acid or VRLA batteries for stationary applications. General rules and proper maintenance. Flooded lead-acid batteries can function for 10 years or longer if properly maintained. The 6 general rules of proper maintenance are: match the charger to the battery requirements. Do not overcharge or undercharge. Avoid over-discharging the battery. Maintain the electrolyte at the appropriate level. Add water as necessary. Keep the battery clean. Avoid overheating the battery. Provide an equalizing charge periodically to the weak battery cells. And that concludes safety. Next we will go into storage and shelf life and inspection. Storage and shelf life. Batteries should be stored indoors between 60 degrees Fahrenheit to 85 degrees Fahrenheit, preferably at 77 degrees Fahrenheit, and should be in a dry location. Place batteries in service before the expiration of its shelf life. This is the date stamped on the shipping carton. Storage duration is 6 months for lead calcium batteries and 3 months for lead antimony and lead selenium batteries stored at a temperature of 77 degrees Fahrenheit. General rule of thumb: for every 15 degrees to 18 degrees Fahrenheit rise in storage temperature above 77 degrees Fahrenheit will reduce the storage time by 50% if constantly held at these higher temperatures. Checking the open circuit voltage. If storage temperature is above 77 degrees Fahrenheit or storage time is beyond the stamped date, measure the open circuit voltage. If the open circuit voltage drops by 0.02 volts below the normal voltage, give it a booster charge. Specific gravity. You can check specific gravity on flooded types only. If specific gravity drops 25 points below the normal value, it is time for a booster charge. Boost charge done at equalization voltages. Boost time will vary depending on the state of charge. Your initial inspections. Inspecting the shipping carton for signs of damage and wetness. File a claim with the freight carrier if you suspect a shipment damage. Note: water will dry, it will evaporate, acid will not. Inspect the cells after removing from the carton. Keep the installation and operation manuals. It contains valuable information. Check the accessory box for its contents. Very important to inspect shipment. And some defects are easier to detect than others. For instance, this would be much clearer to detect problem, a shattered jar. Some are much harder to detect. For instance, a small crease in the box here may be a small crack in the jar. The battery room inspection. Check the local environment. Is it clean, cool, and dry? Is it free of debris? No signs of water, oil, or dirt. What's the ambient temperature? Is it within the operational guidelines? Confirm the room is properly ventilated. Make sure battery cabinets and racks are properly grounded. Check for equipment that can produce excessive heat. Batteries are sized for a specific load, for a specific runtime, for a specific end voltage. Confirm proper load cable sizing. Will they be able to handle the delivered current? Make sure cables are routed as directly as possible from the battery to the terminal blocks. And that concludes our storage, shelf life, and inspection.